Recording. Okay. Bismillahirrahmanirrahim. Okay. First of all, please tell me if you can hear me clearly or not.
Yes, sir. We can hear you
Okay.
clearly.
Okay. Thank you. So now we will be discussing the design of isolated column footing. Last time we covered the design of wall footing. This is very easy if you learn the design of wall footing. So column footing uh, design will not be difficult for you. As you have seen in the first lecture on footing, that isolated column footing consists of an individual column footing, which is generally square in plane, but rectangular shapes are also possible. The behavior of isolated footing is like a slab that directly supports a column. Okay, an isolated footing displays essentially two-dimensional action, cantilevering out in both orthogonal sides of the column, unlike wall footing. If you have seen the behavior of the wall footing, and if you remember, the wall footing basically display one-dimensional action because it is very long in one direction and short in the other direction. So along the short direction, when the soil exerts pressure on the wall footing, so along the short direction there is a bending, which causes tensile stresses in the lower part of the wall footing along the short direction, and compressive stresses in the top side of the footing, and then we design it so that we place reinforcement on the bottom side of the wall footing. However, in the case of column footing, since the column is column footing, the pad of the footing is square generally. So in the case of a square column footing, they'll be bending in both directions, just like a plate. When you place a column or a wooden, let's say a wooden column on a foam which is square in shape, and you push it down, so the behavior of the foam will be like a plate which will be uh, which will bend in upward direction by the pressure exerted by the soil. Okay, so the footing is loaded in an upward direction by the soil pressure, and tensile stresses are induced in each direction in the bottom of the footing. The reinforcement will be placed along both the directions, along this direction as well as along this direction, because tensile stresses will be produced along both orthogonal direction, in this direction as well as in this direction. And now this column footing can be designed by assuming that there are two cantilevers, one cantilever in this direction and another cantilever is along this direction. If the column is square in shape, we'll only design this side, and the same reinforcement can be placed in this side, the same can be placed in this side, and the same can be placed in this side. We will be discussing the design of square footing. So in the case of square footing, we will design only one side of the footing, and the same reinforcement will be placed along all the sides because the sides will be equal. This is a typical column footing. Two dimensions, one is B and the other is L. If both dimensions are equal, it will be L square. Okay, area of this will be equal to L square. The bearing area of the column footing can be calculated by this service load divided by QE, as we have done in the case of wall footing. And then the bearing pressure of the soil will be calculated from factor load on column divided by area required, just like the wall footing case. So it's almost the same with only one exception. You will see now. The maximum factor moment is calculated at critical section, whereas rotated column footing critical section is located at the face of the column. If you remember, in the case of wall footing, this equation mu was equal to QU small b k square divided by 2, and b was taken as 1. But in this case, b is not taken as 1 because b will be the other dimension. If we are calculating bending moment along this direction, so b will be the dimension which will be multiplied with this. This b will be multiplied with this in order to calculate the bearing pressure, per unit length. Okay. And K is the same as was in the previous case, but this can be calculated very easily if this is B, total width of the footing, and if the column size is C. So B minus C will give us the two sides, and one of the sides will be K is equal to B minus C divided by T. B minus C divided by 2. This is total is B, total is B. So when C is deducted from this, you will get the two sides of the footing, and then one side will be equal to K, and the K, then K is B minus C by 2. Okay. The ACI code recommendation. The ACI code minimum reinforcement requirement for isolated column is same as for wall footing, which means it is 0.001, 0.0018. Okay. However, many designers, including myself, recommend to use beam minimum reinforcement for isolated column footing as follows. You should remember this. That according to the ACI code, the minimum reinforcement is the same as was for wall footing, which was 0.0018 BH. But in the case of isolated column footing, it is my recommendation to all of you, and many designers do this around the world, that minimum reinforcement for isolated column footing is calculated using the beam formula instead of the slab formula, which will give you higher reinforcement than the formula used for beam reinforcement. It is very obvious because this is 0.005 and the slab is 0.0018, so it is almost 3 times this if it is grade 40. In the case of grade 60, it is 0.0033, which is almost 2 times the reinforcement that we use for slab. And the reason, what is the reason for this? The reason is that there is no redundancy in the case of column footing, and if anything happens to the footing of a column, and if it settles or if it cracks or it fails due to any other reason, then its rectification becomes very challenging, and it can put the whole structure at risk. And therefore, in our designs, whenever there is a isolated column footing, we place reinforcement according to the beam minimum reinforcement and not according to the slab minimum reinforcement. This is justification for this. Okay. In the case of wall footing is continuous. So in the case of wall footing or raft footing or other combined footing which are continuous, we will use the recommendation of the ACI code, which is 0.0018 BH. But in the case of isolated column footing, there is no redundancy, and in order to design the isolated column footing such that no deficiency or no problem occurs this time in isolated column footing, we place reinforcement almost double of what is being recommended by the ACI code. And the spacing is 3 inch or 18 inch. If you want to ask questions, you can stop me and ask your question anytime you want. Okay. The footing thickness in the case of isolated column footing is generally established by the shear requirement. And this time, it will be two-way action which will mostly govern the thickness of the footing instead of a one-way shear, which we have seen in the case of wall footing. What is the punching shear and how this punching shear will be calculated? The punching shear is basically making a hole in the footing paired by the column. Actually, what happens is that when the column transmit load to the loads to the footing pad, and the footing pad in turn transmit this load to the soil, what happens is that the soil in turn will exert a pressure on the footing pad, and this will be lifted up. Okay, and because of this pressure in the upward direction, the pressure in the upward direction in the column pushing it in the downward direction, it is possible that a hole is made at the perimeter of the column, just like as I've given you this example several times. If a piece of paper is kept, okay, and if a piece of paper is kept on the ground, and if a needle is used to push this paper downward, so it is quite possible that needle will make a hole in the piece of paper. Okay, this can be avoided if the thickness of the piece of paper is increased over overall thickness of the piece of paper is increased, or if the thickness of the piece of paper is increased in the vicinity of the needle, or if the needle tip is increased in size. So this will avoid this punching shear. The same is true for the punching shear in the case of isolated column footing. However, whenever there is a monolithic bond between column and footing, this hole or the punching will not occur at the interface of the column, which means that the sides of the column, the sides of the column, the hole will not be made here. The hole will be made away at a distance of d/2 from the face of the column in the footing. So in order to take advantage of this, the punching shear is calculated at a distance of d/2 instead at the face of the column. This will slightly reduce the punching shear, just like what we have seen in the case of beam shear, where the beam shear was calculated at a distance of d instead of calculating it at the face of the support. So this will be, and the punching shear area will be this one, which is sheared. So the thickness of the footing will be one side of this, and then this parameter, which is at a distance of d/2 from the face of the column, this parameter multiplied by the thickness of the footing will be the shearing area. This can be calculated in this manner. The shearing area, if this total is called as B0, this is called as punching shear parameter. Okay, this is called punching shear parameter. So the area of punching will be which area? It will be this area. This area on all sides, which is equal to C, this whole B0, and B0 is basically equal to, if this side is d/2 and the other side is also d/2, and the column side is C, and let's say the column is also square, so it will be C plus D times 4. B0 will be 4 into C plus D. Okay, and the area which is to be now deducted from this punching shear will be this area, which is one side is C plus D, and this side is also C plus D. This area must be deducted because the punching shear is produced by the pressure of soil on the remaining area, not on this area, because the pressure which has been exerted on this area will not cause shearing at the face of the column. The shearing is produced at a distance of d/2 from the face of the column. So which means that this area, which is the remaining area, will be basically causing the punching shear. So the total area of this, if the total area of this pad is B square, so the upward pressure will be equal to QUB square. The upward pressure will be equal to QUB square. Okay, so this should have been equal to VU. This should have been equal to total critical shear at the face of the column. But since this whole or the shearing does not occur at the face of the column, rather it occurs at a distance of d/2 from the face of the column, so this must be deducted. This area multiplied by QU must be deducted. So this area is C plus D whole square, into QU. This small area shall be deducted. Although it has very minimum significance in the magnitude on the magnitude of VU, as you will see in the example, that VU will be very slightly reduced if we do this. But as you have seen in our several lectures, that this is a permission granted to us by the ACI code, that instead of using QUB shear, which will give you more shear, and in the case of more shear, you will need more thickness. So the ACI code allows us this slight reduction in the punching shear, so that if you want to slightly economize our design by reducing the thickness of the foundation pad, we can do so. Although in our practical design, we do not take any advantage of this because this is of very less significance, as you will see in the coming slide. Anyhow, the punching shear can be calculated by QUB square, which is the total shear, if we are going to calculate shear at this interface. Okay. Hence the
Sir,
please.
excuse me, sir.
Please.
Sir, D क्या represent कर रहा है? कौन सी dimension?
The depth of the footing.
Okay, sir.
Critical depth of footing. So D by 2, which means this total is C plus D, because C is the column and D by 2 on the column side. So every side of this, if it is a square column, will be C plus D. So the area of the blue area can be calculated by C plus D whole square. And when this is multiplied by QU, this pressure can be deducted from the total pressure. This is the idea. QUB square minus QUC plus D square. If you don't do this and QUB square is calculated, even then it will not make a big difference, as you will see in the examples. Okay, then the punching shear capacity. The punching shear capacity in the case of beam, you have seen that it was 5.2 FC prime BWD. But there are two changes. One, the 2 factor has been replaced by 4. And instead of BW, now we have B naught, because the punching shear area is now B naught times D average. B naught times D average. This is the punching shear area. 4 sides of this. So this will be B naught D. B naught. This is B naught. This, and this. The summation of this is B naught. So B naught will be equal to 4 into C plus D. 4 into C plus D. This is B naught. And this multiplied by thickness will give us the punching shear area. So it will be 4 into C plus D multiplied by D. Or this will be B naught D. B naught D will be equal to 4 into C plus D into D. This is the punching shear area. Because this will take place into the column depth. Okay, this area will be detached. So B naught D is the punching shear area, and B naught is the critical shear parameter. And in the case of square footing, B naught can be calculated by 4 into C plus D average. Okay, if 5VCP is less than VU, the depth of footing is increased instead of, as we discussed this in the previous slides for wall footing. Now the steps. The steps are almost the same as we discussed in the case of wall footing. First of all, we will assume the thickness of H, the minimum is 9 inch. Then calculate weight of fill plus weight of concrete. Then calculate QE, calculate area required. If you have any questions, please you can ask for questions. Critical parameter B naught is equal to 4 to C plus D average. Then QU can be calculated, VUP is calculated, 5VCP is calculated then, and then MU is calculated, and AS is calculated in the next step. Then AS minimum, bar placement and draft. These are the steps. Now let's solve this example. Look at this example. There is a column 18-inch square with FC prime equal to 3 KSI reinforced with 8 bars. Of Fy is equal to 40 KSI supports. So this information of FC prime 3 KSI and reinforced with 8 bars of the column, although it will not be used in the design of isolated column footing, this has been provided to us in the example. The column size will be used because in the case of in the calculation of B naught, we will use this column size, because B naught is equal to 4 into C plus D. So column size will be used. FC prime 3 KSI, which is the column strength, concrete used in the column, this will not be used. 8 bars in the column, this will not be used. Fy is equal to 40 KSI, again this will not be used. The things which will be used is the service load on the column, which is 81.87 kip, and the factored load is 103.17 kip. This will also be used. The load is acting at the base of the column, which means at this level. The same concrete and steel is used also in footing, and 40 KSI of strength and 3 KSI of concrete. The same concrete and steel. The allowable cell pressure at the level of the base of the column footing is 2.204 kip per square, which is 1 ton per square foot. Design a square footing with base 5 feet below ground level. Take unit weight of soil as 100 PCA. Column size and everything has been given. Okay. First of all, you will assume thickness of the footing. We assume this time footing thickness equal to 15 inch, and 15 minus clear cover minus 1 bar diameter. And this time we assume that the diameter of the bar will be 1 inch, So 15 minus 3 minus 1 is equal to 11 inch. And then because there will be two bars placed here, one along one direction and the other along the other direction. So if the diameter of this one bar is 1 inch, then 3 plus 1 inch, and we are taking d average. Because the d average will be used for the reinforcement calculation along both the sides of the footing, instead of calculating reinforcement for each direction, because this will be just waste of time and will not give us any meaningful information. So d average will be used for the calculation of reinforcement along one direction, and the same reinforcement will be placed also along the other direction. Okay, so 3 inch plus 1 inch, 3 minus 1, 15 minus this will give us d equal to 11 inch, which this d will be calculated. This d will be basically measured or will be taken from the interface of these two columns, these two reinforcement up to this space, to top of the plate. So this will be d. Okay. W is equal to W concrete plus W fill. It will be gamma fill into Z minus H plus gamma CH. According to this will be 0.5625. We will calculate then QE like this, and the area required is then service load divided by QE, which comes out to 49.86. We assume a 7 by 7 feet footing, 7 by 7 feet square footing. Okay. Then B naught can be calculated by 4 into C plus D average. C is given to us, D is already there, so we have 116 inch B naught. QU, which is factor load on the column, can be now calculated by 103.17 divided by the size of the area of the footing. 2.105 per square foot is the upward pressure. VUP can be calculated now from the equation QUB square. This gives us a 90.85 kip VUP. 5 EC 454 FC prime B naught D average. B naught has been calculated in the previous slide, so it will be 0.75 into 4 into FC prime. B naught is 116. D average is 11 divided by 1000. So the 5 EC value is very high, 209.66, much higher than the critical shear. So the assumed thickness is okay. If you want to reduce the thickness a little bit, you can do this. However, in this example, we will keep the same thickness, 15 inch. And we will calculate now QU, which MU, which is QU B K square divided by 2, K is B minus C divided by 2. Total B 7 feet, 7 into 12 minus C 18 inch divided by 2 is 33 inch, which is 2.75 feet. So this is 2.75 feet. And then the dimension along the other side, this dimension will be equal to B, this is 7 feet. So 2.105 into 7 into 2.75 into 2.75 W square, K square divided by 2. This gives us a bending moment of 55.72 foot kip. You can convert this into inch kip like this. Then by trial and success, you can calculate AS. If small age is zoomed equal to 2.2 inch and the trials are done, then the AS comes out to 1.71 square inch. But we will then check against the minimum reinforcement, which is 0.005 BD average, which is much higher than the reinforcement required. We will use this one, minimum reinforcement. And in the case of isolated column footing, you should listen to me very clearly and loudly. I'm telling you that the AS minimum in the case of isolated column footing will be most of the time greater than the area of reinforcement required, actually required. So the minimum reinforcement will mostly govern in the case of isolated column footing if the area of reinforcement is calculated based on 0.005 BT average. In the justification part, this I've already given to you. Next, the placement of reinforcement. Now the bar will be placed in this. The total area of steel is 4.62, and the diameter of the bar, this is number 8, which has an area of steel equal to 0.8. So divided by this, which will give us 6 bar, 5.661, but 6 bars will be needed. 6 bars will be placed now in 7 feet spaces, and if 6 inch is placed on one side, left on one side, 3 inch, 3 inch is left on one side and 3 inch is left on another side, we have total 6.5 feet space available to place the 6 bars. So 6.5 divided by 5, which is the number of bars, number of spaces, will be equal to 15 in center to center. So 15 in center to center will be places. 1, 2, 3, 4, 5 spaces. Bars are 1, 2, 3, 4, 5, 6. So 6 bars will be placed at the rate of 15 in center to center. Okay. Then the next, please. Any question?
सर ये हमने शुरू में एज्यूम किया एच, तो एच की वैल्यू हम कौन से रेंज में एज्यूम कर सकते हैं?
एच की वैल्यू 12 इंच से कम आप आइसोलेटेड कॉलम फुटिंग में न करें, 12 इंच से बिल्कुल कम इस्तेमाल न करें, और उससे ज़्यादा तो जो भी आपका कैलकुलेशन से आ जाए वो आप एज्यूम करें। इसमें 15 इंच हमने एज्यूम की, तो हम थोड़ा सा इसको कम कर सकते थे 12 इंच, लेकिन हमने नहीं किया है। अगर आप इसको मजीद इकोनोमाइज कर चाहते तो आप 1-2-3 इंच और भी कम कर सकते हैं। लेकिन जिस तरह मैंने कहा कि आइसोलेटेड कॉलम फुटिंग में रिडंडेंसी बिल्कुल नहीं होती है, तो इसमें हम सेफ्टी फैक्टर काफ़ी ज़्यादा रखते हैं। अगरचे कोड आपको अलाउ करता है कि आप रिइंफोर्समेंट स्लैब वाले इक्वेशन से मालूम करें 0.0018 से, लेकिन मैंने आपको कहा कि आप 0.005 से मालूम करें, बिकॉज आई हैव सीन नंबर ऑफ आइसोलेटेड कॉलम फुटिंग फेलियर। मुख्तलिफ रीज़न है, उसकी रिइंफोर्समेंट तो नहीं है, लेकिन बाकी रीज़न होते हैं। इस वजह से थोड़ा सा कंजर्वेटिव साइड पे ये डिज़ाइन हो जाए तो अच्छी बात है। इसलिए थिकनेस भी इसकी आप थोड़ी सी ज़्यादा रखें तो ये बेहतर है। ये इसकी फाइनल ड्राफ्टिंग हो जाएगी। ये एक एग्जांपल है आप लोगों के लिए, इसको कर सकते हैं खुद। दिस इज द एंड ऑफ दिस लेक्चर। इफ यू हैव एनी क्वेश्चन यू कैन आस्क योर क्वेश्चंस। आप क्वेश्चंस करें, और इसके बाद हम लेक्चर नंबर 5 जो कि चंद स्लाइड्स हैं, कुछ सर्विसिबिलिटी इशूज है, वो डिस्कस करें। प्लीज आस्क योर क्वेश्चंस। आई विल वेलकम योर क्वेश्चंस प्लीज। ये आप लोगों ने देख लिया कि इट इज मोर और लेस द सेम एज it is more or less the same as wall footing. You have seen in the case of wall footing all these equations, so it will be very easy for you to understand this. Still, if it is not clear to you, you can ask your questions, please. Any question?
सर जरा वो मिनिमम रिइंफोर्समेंट वाला जरा रिपीट कर देंगे एक दफा, कि वो आपने कहा था बीम वाले डालने हैं और स्लैब वाले नहीं डालने हैं, तो वो जरा रिपीट कर देंगे।
जी क्या बताऊं, दोबारा पूछें।
सर वो जो आप मिनिमम रिइंफोर्समेंट की बात कर रहे थे, जरा वो रिपीट कर देंगे। वो आपने कहा स्लैब वाले नहीं डालना, बीम वाला इसमें मिनिमम रिइंफोर्समेंट।
हाँ, वो मैंने इसलिए आपको मैंने वो ये कहा कि आइसोलेटेड कॉलम फुटिंग तो में कोई रिडंडेंसी का मतलब ये है कि इसके ऊपर कॉलम है और कॉलम के नीचे एक पेड़ है। अगर इस पेड़ को कुछ हो गया, सेटलमेंट हो गई या रिइंफोर्समेंट को करोजन हो गई या कोई और प्रॉब्लम आ गया इसमें, तो ये जब सेटल होगा तो तमाम कॉलम्स को नीचे वो पुश करेगा और अपने साथ नीचे ले जाने की कोशिश करेगा, और उसके स्ट्रक्चर में काफ़ी मुख्तलिफ किस्म के क्रैक्स आ सकते हैं। तो इसमें चूँकि आइसोलेटेड कॉलम फुटिंग, हम सिर्फ एक कॉलम फुटिंग जो इंडिविजुअल का हर इंडिविजुअल कॉलम फुटिंग के ऊपर हम बहुत ज़्यादा रिलाई करते हैं, और कॉलम फुटिंग तो आपको पता है इट इज़ बरीड इन द ग्राउंड। तो इसमें हमें बाद में पता नहीं चलता कि इस फुटिंग के साथ क्या हो रहा है। तो इस वजह से मैं खुद ही करता हूँ, और कुछ डिज़ाइनर्स और भी हैं अराउंड द ग्लोब, वो भी इस तरह करते हैं कि आइसोलेटेड कॉलम फुटिंग में वो रिइंफोर्समेंट बीम वाली मिनिमम रिइंफोर्समेंट डालते हैं 0.005 जो आपको याद होगा, और 0.0033 ग्रेड 60 के लिए, 0.005 ग्रेड 40 के लिए, जो कि हम बीम में मिनिमम रिइंफोर्समेंट इस्तेमाल कर देते हैं। एशियाई कोड आपको स्लैब वाली मिनिमम रिइंफोर्समेंट अलाउ करता है, अगर आप इस्तेमाल करना चाहे तो आप कर सकते हैं, लेकिन हम इस तरह नहीं करते। हम बीम वाली मिनिमम रिइंफोर्समेंट इस्तेमाल करते हैं, क्योंकि अनलाइक द अदर फुटिंग, जैसे कि कंबाइंड फुटिंग है या राफ्ट फुटिंग है या स्ट्रिप फुटिंग है या वॉल फुटिंग है, उसमें आपके पास काफ़ी रिडंडेंसी होती है। एक जगह अगर कुछ हो जाए तो बाकी जगह उसको संभाल सकती हैं, जबकि आइसोलेटेड कॉलम फुटिंग में इस तरह नहीं।
थैंक यू सर, थैंक यू
सर। ये क्वेश्चन में ना वो सर्विस लोड कम तो इफेक्टिव लोड ज़्यादा था।
हाँ, तो इस तरह होता है ना, सर्विस लोड तो अनफैक्टर्ड होता है ना, 1.2 1.6 के बगैर होता है, तो कम ही होगा, और फैक्टर लोड उससे ज़्यादा होगा, क्योंकि उसमें इफेक्ट आ जाता है। ठीक है, एनी अदर क्वेश्चन? प्लीज। कोई और क्वेश्चन है जी आप लोगों का?
नो सर।
चलो ठीक है, फिर हम दूसरा लेक्चर शुरू करते हैं एक 5 मिनट ब्रेक के बाद, ठीक है?
यस सर।